had have been all about building up upon what we had initially learned about forces and electric fields, right? Looking at the other side of things. The general order that we seem to be doing things in physics seems to be we talk about dynamics, and then forces, and then different ways that we can cause those forces, and then we start to talk about energy, and then we start to talk about that relationship between forces and energy. And we're kind of following the same track here. We don't need more dynamics because, of course, we've already done dynamics and there's not electric velocity or anything, but there is an electric force, and we grew upon that idea of force by talking about something like the electric field, and then we tied that over into electric potential energy and electric potential, and the potential is to potential energy what electric field is to force, right? It's essentially separating out that second charge. It's waiting for another charge to be there. It's telling you how something interacts with anything else around it, how we could predict that to happen, but we don't need the second charge to actually be there yet. Right? We can predict what it would do if we put something else here, and the fact that it's a field and goes out into space means that we can describe any point surrounding our object. So that was useful. But then we started to take a look last time at how we can actually tie together these electric field and electric potential ideas. Right? Surely there's a connection between forces and energy. We have seen such connections before. But it kind of follows in the exact same way that we can do the exact same thing with electric field and electric potential, because really all we did is divide by a charge, right? We divide by Q2 and we get field and potential instead of force and energy. So today we're going to continue that a little bit, but most of our interest is actually going to be towards capacitors, devices which use that electric potential in some way or another to store charge. But before that, let's go ahead and dig into a few concept checks covering a lot of material from last time. So I have a graph of the potential, and I've got 2 points marked out, A and B, and I've made them a little bit larger because I know earlier today we were having a few issues with connectivity and it was a little bit hard to see some things. But which point has the stronger electric field? Interested in magnitude only, not worried about direction. So let's think about it like this. So last time I threw this kind of strange equation at you, right, with a brand new symbol that we had never seen before called del. And there should be a negative sign out front of that thing. But del seems a little bit strange and complicated at first when you look at its definition, but really what it's doing is it's trying to take derivatives and it's trying to separate those derivatives out into directions. That's all it's really doing. So in a case like this, when we're looking at just x, we don't need to worry about the full del equation. We just need to focus in on what's going on with x. So we could say that the x component of the electric field is equal to the negative derivative with respect to x. All that's really asking me for is the slope, right? So I'm going to look at these two spots. I'm going to say, okay, right here at A, right here at B. For A, my slope is roughly, I'll keep doing this color, something like this. And that's not a fantastic drawing, but we can kind of get an idea of what that slope might look like. Versus out at B, my slope looks something more like this. The negative sign out here doesn't actually make a difference for us. Because again, we're looking for just the strength of the electric field. And if we're just looking for the strength, that's really just asking for magnitude, not actually worried about whether it's positive or negative. So the steeper slope is going to be where we have the stronger electric field. X of A is going to be our winner for this one. Okay, let's take another look at another one of these. Oh, bouncing around all over the place. I'm going to make this one a little bit bigger because these dotted lines are kind of hard to see on Zoom, I think. Hopefully they're a little bit better for anyone watching on Twitch. But what I've got here, we can read the problem before I do that. Which set of equal potential surfaces matches the electric field? So what I've got in this light magenta color is my electric field. Direction and strength are important here. Which of these 6 options of equal potential surfaces would actually match and recreate this type of electric field? Take a minute or two and look over this one, because there's a lot to pick apart, but you can do a process of elimination to to help out, make this whole thing a little bit easier to deal with. So, let me think about it like this. And I'll start this thing in black. So if I'm looking at this thing, if I'm looking at my electric field and I'm thinking about, okay, well, I'm getting weaker as I go to the left side. Strongest on the right side, pointing to the left, getting weaker as I go farther left. That suggests to me that we're looking at something, if we had to see the charges, if we got the opportunity to see what charges were actually creating this field, I would take a gander that it would be something like this. Right, where I've got positive charges on the right side, and then nothing over on the left side, because it's going to get a little bit weaker, and this is not an infinite plane of charge or anything. But I've got a group of charges, and it's strongest near those positive charges. It's pointing away from the charges because they're positive, and it gets weaker as we go out. Okay, then right off the bat, what that would tell me, if I had a field, if I had a group of charges that looked like this, then what I'm expecting to see here is a high potential on the right side, a low potential on the left side. That one's out, that one's out, that one's out. All three of those are backwards from what I've just described. So then, we've only got three options left, which makes this a little bit easier to deal with, right? Now, the first thing that I'm going to look at here, if I am observing what's going on in A, this one's a little bit strange, it's a little bit unique, because what we see here is evenly spaced equal potential lines. We don't always get something like this, and it's kind of a rare occurrence when this happens, but what this is saying, if you think about this, equally spaced lines tells you that it's a constant slope. Right? We only ever get this if we have a constant slope. If we go back to this picture, for example, if we had something that looked like this instead, what you're doing with a constant slope is you have regular tick marks on your y-axis. And they're showing up equally spaced every single time, right? It's a linear slope at that point. So what that suggests, if it's a linear slope, if it's a constant slope, then this would give us a constant electric field. Constant electric field is simply not what we have here. This one's out. So now we're stuck between B and C. Well, I'm going to kind of go along with that same description, right? If I'm thinking about where's the steepest slope, where's the steepest slope that we could possibly have? Well, that's going to be where we see the tightest bunch of lines altogether. Right? Because I can say that, okay, well, that's 10 volts, and that's 20 volts, and I know that's a little bit hard to see on the screen, and then 30, and then 40, or something like that. I don't think they're evenly split, are they? They're in some weird, nasty, like, they're divided by 6 or something. Yeah, something stupid like that. We're not going to worry about that. But the point of it is that when they're tightly bunched, that's where we have the greatest slope. Right? That's where the most change is occurring all at once. So if we're looking for where is going to be the greatest change all at once, that's going to be giving us our strongest electric field. If we see the greatest change on the right side, we should be expecting the greatest field on the right side. C is out. Actually, let me do that backwards. C is out. B is the right answer for this one. So high potential versus low potential, it's always going to be, the field always points from high potential to low potential, is really what we would see here. If I didn't go with this description of charges, I shouldn't need to draw out where the charges are on this thing to make this picture happen. What I'm really looking for here is that the electric field will always point from high potential to low potential, because that equation, electric field is equal to the negative of the gradient of the potential. Del is really telling you about the gradient, which is a term that we don't hear very often, but if you're thinking about any times if you drive in any hilly areas or anything else like that, if you hear about a steep gradient, the reason they use gradient instead of slope is because gradient is essentially slope but in 3 dimensions. Right? Slope is specifically, most of the time at least, for when you've only got some sort of 2-dimensional graph like this, y versus x, but a gradient tells you about 3D shapes. So the steepest gradient is going to be where there's the most change all at once. But because we see a negative sign here, we're saying, okay, well, the opposite direction from the slope. So electric field is going to start at high potential, go down to low potential. That's the direction that the arrow should be pointing. Absolutely. And again, that can be going in either way of whether it's going from 50 to 0 or 0 to negative 50. That would be equivalent. If we relabeled these, if this was negative 50 and this was 0, it would still work out just fine because it's about that change of the potential. That's the most important bit. Almost. The trick, so the question is, couldn't we think about equations for the electric field and voltage because both have R in the denominator? Almost, but the trick of it is that the negative sign makes things a little bit weird. So you can do that for strength of the electric field, because then the negative sign doesn't matter. Then you're just thinking about a magnitude, but if you're actually considering the direction as well, you've got to flip things like that. And that, yeah, that's where it gets a little bit tricky. It's possible, and I know that everybody has their way of remembering things, and if that's the way that works for you and you just know that it flips at the end, go with it, right? I always like to think it's, I imagine it's the hill, right? At the very top, that's where my high potential is, and the valley, that's my low potential, and the electric field is going to roll down to the bottom. Okay, let's try another one here. Here's one with a few more numbers to them. And I will tell you right here what we've got already drawn on this thing. This will give you some help. This is the electric field, right? That is, it's a representation of what the electric field is doing. So it kind of eliminates two of the answers right off the bat. But aside from those, what is the electric field at this dot? So, kind of like when I was describing this last one. Right, we're looking at our scenario in green here, right? Our constant electric field, equally spaced equipotential lines, means that we have a constant electric field, right? If we were actually to graph out what the potential would look like, potential versus X, we're seeing something like this. So, or I guess something like this in this case, right? It's going down as we go farther in X. But I'm not as concerned about that as I'm interested in the fact that it's linear, right? And being a linear graph means that if we're thinking about that electric field, you can say negative dv dx, because I'm looking at the x direction here. And this would be fine if I wanted to look at potential, or if I wanted to actually calculate this thing out and take a derivative and all that good stuff, but I don't really want to take a derivative. I don't want to create what this function would be, find where the intercept is supposed to be, and then take a derivative of that, when instead what I could say is, hey, remember that big point of calculus that the derivative is looking for the slope at a particular point? And if the entire thing is linear, then that means we don't have to worry about any one single point because the slope is the same all the way over. So instead of thinking dv dx, we can think delta v over delta x. And it doesn't matter where I pick this thing now because, once again, we're looking at a constant electric field. So I'm just going to pick between 0 and 2 as my 2 points. Then what I can say is, okay, well then my electric field should be the negative of final minus initial, 20 minus 40, over final minus initial is 2 minus 0. I end up with 20 divided by 2, 10 volts per meter. Now, that negative sign was a little bit important here, right? And we could have figured out what the direction of the electric field should have been by looking at our picture, but it's good to think about it mathematically as well. When you're taking your final and initial points, since I said this is I and this is F and I'm going this direction, the fact that I got a positive value at the very end tells me, and I know that's a little bit low, that says 10 volts per meter. You can see the 10, I think. But the fact that it's a positive 10 volts per meter tells me that my electric field is pointing in the direction of my path. If I'd done that backwards, I would have gotten the same result, but it would have been negative instead. And that would have said, hey, my electric field goes the other way. So keep that in mind, right? Think about what you're doing with that path, that initial to final. Does this one work for the previous question? The same kind of approach? Yeah, in a sense. Yeah. The only problem with this last question was that we didn't have any sort of we have relative magnitudes, right? We have strongest to weakest. So that's kind of what I'm doing here, but because it's constantly changing now, I can't just imagine that it's a linear slope anymore. I can't quite do the same thing. But it's the general trend that I am sticking with as well. Yes. So, one last concept check for now. But let's imagine, so I've got some no longer as clean, some wavy equipotential lines. I start from position I go to position F. What is the potential difference along my path? What do we think? So, here's what we've got. The electric force is a conservative force. That means that it is path independent when you're thinking about work and potential energy, right? A lot like gravity, it doesn't matter how you got to that point. Your potential energy at that point only depends on your final position, and it doesn't care about the path you took to get there. So here, even though I dip down to positive 50 and then go back up to negative 50, it doesn't matter what path I took. I could take a path that goes like this, circles around, it gets to my final point. I could take another path that goes in some other crazy direction. It does not matter. The only thing that matters is the difference between our final and our initial. And in a case like this, we end at negative 50, we start at 0, final minus initial should land us at negative 50 volts for this one. Right? It's kind of a neat thing that because the force is conservative, we also have all of these other ideas, the electric field and the potential, all of these other things should also be path independent. It makes the problems much easier to deal with. Right? Instead of having to constantly worry about something like friction, you know, the electric equivalent of friction or something, that would be kind of that'd be a mess. Let's keep chugging right along then. So I keep talking about these potential lines and equipotential lines and all this good stuff, but where does it actually come from? Well, surely it comes from positive and negative charges, right? That's how we've been talking about it so far. But realistically, how many times have you plugged in some new positive charges into your controller? I'm willing to bet not very often. Instead, though, batteries are a very common thing, right? We use batteries all over the place. Your car has a battery, your remote has a battery, your controller has a battery. A lot of things have batteries, right? What are those doing? Well, they're actually providing some sort of potential difference. And that's kind of an interesting thing because it's not necessarily that they're supplying a potential. Like your wall socket, for example. It's not necessarily true that one side is 0 and the other side is 120 volts. In fact, sometimes it gets a little bit off from that. And sometimes you'll have objects with that third plug, the ground plug, that connects to typically a water pipe in your house. And that one is always supposed to be close to 0, but the idea of that is that it goes, you know, it's an emergency place to throw a lot of charge as needed. But the point being is that a lot of your devices don't necessarily run on any particular potential. Instead, they run on some sort of potential difference. And that's what actually needs to be provided. And I think I've brought this up before, but when you're talking about something like getting away from a downed power line, like let's say you're in some sort of accident, it's a stormy night or something, and there's a downed power line, and you are, for one, don't get out of your car, but you're out of your car anyways because you've forgotten this lecture, and you need to get away from there, right? Because of course there's fire and plasma and sparks and a bunch of other terrifying and from a distance very cool things from a downed power line. So what do? You don't run away. Probably shouldn't hop either. The best approach is to very, very, very slightly shuffle your feet back and forth going forward. making sure that there's not much distance and going directly away from that downed power line. Or maybe at an oblique or something like that. But the point is, you're trying to move away and you're trying to shuffle your feet the entire time. And the big reason for that is because it's not the fact that it's 2000 volts. 2000 volts is actually fine as long as there's not somewhere else that's zero. It's the potential difference that matters much more than what the potential actually is. And the potential difference is going to be what drives most of our circuits that we're seeing in day-to-day life. So this is kind of where this term electromotive force comes from. It's outdated. I don't like it. I'm not a huge fan. I would much rather just say potential difference, but a lot of people still use EMF, so I've got to bring it up anyways, including the problems that we're going to be working on. But the electromotive force is essentially you create a potential difference. That potential difference means charges move. EMF. So most of the time you'll see this as just an abbreviation of a source of EMF. We don't often call it by its full proper name. We just say EMF or potential difference. I like potential difference the most, but EMF is probably just, it's kind of deep-seated at this point. So, for example, like a car battery would have 12 volts or something else. There's all sorts of fun things that go into this. But we'll be using these sources of EMF plenty, right? And you've got a lab that actually goes with the lecture from today where you use a battery to charge up a capacitor and to set a potential difference inside of a capacitor. So a useful thing to have, right? Of course, we use batteries everywhere, as I've said before. So what about something that's not quite as good as a battery? Charged conductors, we have talked about plenty at this point, but every single time we've talked about them, we've always been looking as to when they are symmetrical and easy to describe. Real conductors, those that are not such perfect spheres, maybe weird triangles or anything else, don't quite behave as nicely as our perfectly symmetrical ones. Right? There's a couple of big factors that are going to start to change, actually. For one, if I have something like what I've got here, this triangular shape, what I'm actually seeing here is I'm not going to have a uniform surface charge density. All of the excess charge is still going to be stored on the surface of this object. The electric field inside will still be zero. Those are two details that have not changed. But the surface charge density is not necessarily equal throughout. And the reason being because what does need to be equal is that potential. The potential across the conductor has to be zero because, again, if there's any potential difference, that's going to be what causes charges to move. So as long as there's a potential difference on a conductor, charges are going to move around until everything is settled, everything is uniform, the potential is even all the way across my shape. So what does that mean for our electric fields and for the field lines and the equipotential surfaces? Well, we might see a little bit of an intensity spike towards edges and corners that are jutting out like that because they will have more charge built up on them. But more than that, and this is something that I brought up in the last lecture as well, what we see for a lot of these things, I'll blow this up a little bit, is that the electric field lines relative to the equipotential lines are always going to be perpendicular. Right? If we're looking at this, every single one of these lines in this magenta color is going perpendicularly to the equipotential line. And you can kind of imagine it. Let's think about that hill and valley description again. If you are a speed skier, which way are you going to go? Are you going to go straight down the slope, or are you going to meander back and forth and slide side to side? No, that's much slower, right? You're taking a much longer path. You never have as steep of a slope. The way you get the steepest slope is by going straight down. That's what the electric field does every single time. The electric field line is always going to be perpendicular to the equipotential lines that we see. It's just how you get the greatest slope. It's what it means to take the gradient, which this is essentially taking the slope, but in more dimensions than just one. If we were still graphing this out, it would be taking a derivative like normal, but actually drawing out the gradient symbol is you're looking for the slope, but you're looking for the slope in all directions. When you take all directions into account, the steepest slope is the gradient. And that's the actual rate of change of the potential. So let me make that a little bit small. Oh, let's move. There we go. Okay. So let's try this out in a problem. This one's going to be a little bit strange. I've got to give you a warning right off the bat. So I've got two metal spheres. Metal sphere 1 is initially charged with 6 nanocoulombs. Metal sphere 2 has twice the radius of metal sphere 1, but has no charge on it when we start. So 6 nanocoulombs and 0. I attach a very, very, very tiny wire between the two, right? It's very, very thin. And that allows some charge to move back and forth between those two. What is going to be the final charge on my second sphere? Keep in mind, the charge on each one does not necessarily have to be equal. The charge density on each one does not necessarily have to be equal. There are a couple things that do need to be equal, though. And that's the challenge to figure this problem out. Okay, how's about we start to take a look at this one? Let's draw this thing out first. One sphere, two sphere. We will color them in with a light gray so that we know that they're conductors. We'll put some lines in here, and this was not very well drawn to scale, but you know what? That's okay. So we're going to call this one R and this one 2R. Now, what we have initially is that this one over here, in orange, please. Thank you. What we initially have, Q1 is equal to 6 nanocoulombs. So what we know here is that this 6 nanocoulombs is going to split up among the two, right? So this is what I start with, and then I attach a very thin wire between the two. So thin that there's not going to be really any charge on the wire itself, but it does allow some charge to transfer between my two surfaces. What I'm left with is what I'll call little q1, a piece of the charge 1 and a piece of the charge 2. All in all, I know that q1 plus q2 has to equal my initial charge because I don't have any other source of charge. There's nowhere else for it to go. There's no more charge coming in. So they have to sum to my initial charge, but then there's one other thing that we also know. And it's the fact that because these are two conductors connected, the potential across the surface is equal everywhere. If there was any discrepancy in the potential, if there was any difference at any point, if my second object had a little bit lower potential of any sort, charges would move from the sphere 1 over to sphere 2 until the potential was equal all the way across. So the other thing that I can write here is that V1 is equal to V2. Now, this is where it gets a little bit strange because we have to think about, okay, well, how do I describe the potential on these spheres? Well, remember, anytime I see a sphere that has charge on it, it's behaving a lot like a point charge. Right? Gauss's law told us that anytime I've got a sphere with charge, it behaves just like a point charge as soon as I'm outside of it. As long as I'm not looking inside of that object, it's going to behave just like a point charge. So if I'm looking just at the surface of these spheres, then I can say, okay, well then they're behaving like point charges right on the surface. That is to say, the potential is equal to K Q1 over R for sphere 1, and K Q2 over 2R for sphere 2. Because I'm looking at the potential on the surface, right at that distance away from the center. So from there, I'm going to say, okay, cancel out the K's, cancel out the R's. Q1 is equal to 1/2 of Q2, or Q2 is equal to 2 times Q1. Go back up to my equation in this burgundy kind of color. Q1 plus 2Q1 is equal to 6 nanocoulombs. Q1 is going to have 2 nanocoulombs. Q2 will have 4. It does end up being a ratio of the diameters here. Yeah, in this case specifically, it does. And I'm trying to think if that would be, for any spheres, you would see something pretty similar. Actually, but only because both of these go as a 1 over r kind of deal. So whatever that radius of the object was. Now, if we had something like cylinders, it might look a little bit different. Right, but yeah, but for spheres in this case, yeah, it is just a ratio of the two diameters. So, speaking of objects with charge, our good friend capacitors. Every time we've talked about capacitors so far, I've always prefaced it with parallel plate capacitors, right? But that doesn't necessarily need to be the case all the time. You can have other objects act as capacitors. And in fact, I was bringing this up in the last lecture. There's a very, very, very cool experiment. I think it was in like the American Journal of Physics or something in the 70s. It was one of those old science journals that had something for a try it at home kind of deal. They had all sorts of crazy experiments, and they were not super user-friendly. Like, they typically required some equipment that's a little bit hard to get a hold of. But this one in particular has always stuck in my mind because it's a really cool thing to build. But what they do here is you take a large sheet of steel, and then you lay a sheet of rubber on top of that. So rubber is an insulator, right? It insulates both in heat and in electricity. Then you take 2 more squares of steel and you set them on top of that rubber, and you take a copper wire and spiral it around and connect those 2 plates. And then you attach a penny to the top and bottom plates on the right side. And it has to be an old penny, so it's got a lot of the copper still in it, right? The old pennies, the newer pennies don't have that same, they're not made of the same materials. But then you would attach the top and bottom plates to a high voltage power supply. And high voltage power supply, we're talking 200, 300 volts, something like that. You know, enough that you don't want to mess with it too much. You want to be careful with what you're doing. But what you're essentially doing is you're creating a very large capacitor between the top and the bottom plates, right? And these are certainly no longer just parallel plate capacitors in the same way, because we've got this weird thing going on here at this point where it's 2 broken plates and everything else. But to finish out the rest of the story, the really cool part about this is that once you got it up, not in class, and I don't know if I would recommend it to anyone unless you're ready to deal with high voltage objects. If you know how to be safe with it, you can absolutely build it. But the entire point of this thing is that you might remember when we were talking about like the breakdown voltage of air, or that electric field that you can create. And if you have a strong enough electric field, the air becomes a plasma and it allows conduction through. You ramp it up until you reach that breakdown voltage between the 2 pennies, and it's what's called a spark gap. Once it reaches that high enough potential, the spark gap activates, you get a bright flash of plasma on that side, and a bunch of the charge on the right plate goes down into the bottom, right, where it's grounded. So now what I've really got is 2 plates side by side at very different potentials, and the fact that the wire connecting them is in a spiral loop means that the current between going through that wire actually slows down a lot, which is something we'll talk about very soon in the course. So you've got this really, really high potential difference between these 2 plates, and what you do is you create a pulse laser out of the nitrogen in the air with that potential difference. Super fun thing. A non-standard use of a non-standard capacitor. The whole moral of the story here, aside from the fact that creating open-air lasers is incredible, is that it doesn't just have to be 2 parallel plates to make a capacitor. You can have other orientations of objects. You can have some strange lumps like what we see on screen right now. Right? What I've got on the screen right now is a positive charged lump and a negative charged lump, and they don't look like the same lump, and they're strange, but there's a potential difference between them, and there's an opposite charge on each one, and that has a value that we will call capacitance. Capacitance is an object's or a pair of objects' capability to store charge given a particular potential difference. So larger objects are going to generally be able to store more charge, right? That's what this whole big thing is about in the first place. But it doesn't require us to have two separate plates. We can do this with any two objects, right? When we're looking at over here, something like what we see in this pair of objects, that can act like as a capacitor. The most important things that we need to know are the charges and the potential difference between those two objects. That's what creates a capacitor. The units for this is something called farads, and we're going to be looking at very, very small values, right? I actually have a few capacitors here with me. Hopefully that's not too incredibly loud. But let me pick like one of these ones. This is a good one to have. So this is a 0.22, and I think that's right. All of these have been unsorted. 0.22 microfarads, and it gets an object that's that big. Right? So think about the size of a lot of electronics and everything else. A lot of electronics are very, 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 very tiny. So this is comparatively a massive capacitor, 0.22 microfarads, a very tiny amount. So expect a lot of these things, picofarads and nanofarads. We're going to be expecting a lot of those values. You can get larger than that, and in fact, the largest ones that I've got in this box are something like this. It's a little bit larger as compared to the first one that we just saw. Oh, it's stuck in there now. They're all tangled together. But this is only 1,000 microfarads, right? So these things, to get up to a value like 2 farads, they do sell those, but they are as large as my arm. They're huge. To get up to single digits of farads, you need a massive capacitor. So, speaking of capacitors, though we can technically make them out of any pair of objects, or any pair of conductors, I should say, parallel plates are still going to be king for us, right? They're so useful to have. They're very easy to quantify. You can shove a ton of charge on them, and it's still commonly used everywhere. In fact, this right here, the object that I have in my hand, even though it's in a cylinder kind of shape, and you can kind of see that, I hope, but even though it's in a kind of cylinder shape, this is still technically a parallel plate capacitor. If you have a desktop computer, if you have some sort of window or some way to look inside of that or anything else, you might see a lot of these small cylindrical caps, and that's what we call them typically. We abbreviate everything. But you'll see a bunch of small caps, and oftentimes they're in silver or gold when they're on computers. And maybe a little bit smaller than these ones, but you'll see those kind of everywhere, right? They're very useful things to have. Not everything needs to have the tiny capacitors. Sometimes we use the larger ones. But what's happening inside of here, because creating large plates is difficult, and well, it's not that it's difficult, it takes up a lot of space. Instead, what they do for a lot of these things is they will take two parallel plates and they'll like spiral them together like a snail shell. And by spiraling them together, you get a much, much smaller footprint while still getting that very large size that you need to have the greatest possible capacitance. Old TVs can kill people with their capacitors? Maybe. I'm trying to think here. Maybe. So one of the things that I can imagine, old TVs, old CRTs specifically, right? Flat screens are a little bit of a different scenario. Flat screens have very large capacitors inside of them for the startup, on the order of... I keep forgetting the one. I think I had I said a different number in the last lecture, but it was a huge capacitor. It's the biggest capacitor I've ever had to actually handle myself. And I want to say it might have been 220 millifarads. It was massive, right? Bigger than my thumb. If I'm thinking about stuff like old CRTs, it's a cathode ray tube is what CRT stands for. And it's quite literally an electron gun. It's like literally what it is. It's an electron gun. It's constantly ripping electrons off of atoms and shooting them. And then you have a very, very strong electric field that redirects that electron to a particular color of pixel. And that's why if you ever try to take a camera shot of a CRT, you get the scan lines because the frame rates don't quite line up and the CRT is constantly scanning across the entire screen. To do that, though, to get ripping off the electrons from different objects, though, it does require a very high potential difference. And I'm trying to think if the capacitors were fully charged, would that cause any issue? Maybe. I'm going to say don't fiddle around with CRTs unless you know what you're doing. Or at least are willing to claim responsibility for not knowing what you're doing. I haven't played around with CRTs a ton myself, but I fiddled with them a little bit. But I'm not going to claim to be an expert by any means. But speaking of large capacitors, how do we make large capacitors? Well, there's two big factors that really are going to tell us about the capacitance of any of these parallel plate capacitors. And it's the surface area that I can pack a bunch of charge onto and the distance separating those two plates. Plates that are closer together are going to have a larger capacitance. And part of the reason being is that if I think about what happens if I've got a bunch of positive charges on one hand and a bunch of negative charges on the other, right? If they're very close together like this, there's an attractive force between them, right? Those two plates are just dying to get together. If they had just one conducting line between the two, all sorts of charge would transfer between them. But there's a lot of force keeping those charges on the plates, right? There's an attractive force keeping them there. Now, if I separated those out, now that attractive force keeping the charges on the plates is much smaller, but there's still a lot of repulsive force among the plates themselves. There's all of these positive charges on this plate that really don't want to be next to each other. And without the attractive force from the negative plate, they just are a lot less happy to be in that spot. There's a lot more repulsive force. So keeping those plates very close together can increase your capacitance. So, and we can also describe what the potential and what the charge on a capacitor could be from those quantities just as well. Right? Just using these equations that we've got so far. So, and this will be a quick whiteboard problem, but I've got two spheres, one charged at positive 20 nanocoulombs, one charged at negative 20 nanocoulombs. There's a potential difference of 100 volts between them. This is not a parallel plate capacitor. I keep saying conductor in place of capacitor. This is not a parallel plate capacitor. What is the capacitance of this pair of objects? All right, and I meant it when I said only a couple minutes on this one, because it's actually really, really quick, right? I don't even necessarily need to leave the page on this one. When I'm looking at something like this, if I actually had to find what this potential difference would be, this would be a much more difficult problem. I'd have to consider a few different points, and to be honest, there might become some difficult things. Because we're dealing with spheres, it would be a little bit easier, but if we were actually to calculate out what this potential difference would be, we would have a real rough time of it, right? Because my equipotential lines would look something like the weird blob that they were coming from, and we don't have any nice symmetrical shapes and all sorts of nasty things. So we're in luck that we already know what that potential difference is, but since we already know what that potential difference is, there's really not much more work to the problem. Take that definition of capacitance. C is equal to Q over delta V. 20 nanocoulombs divided by 100 volts. Let me write out the right numbers first. So 20 times 10 to the negative 9th divided by 100, we should end up with something like 2 times 10 to the negative 10th farads, or if I wanted this in my proper unit, 200 picofarads, as it's asked for in Canvas. So keep in mind, capacitance is always going to be from a pair of objects. I need to have two separate objects to have a capacitance. Otherwise, it's just me putting charge on an object. So it's the pair of them together, since I have positive Q and negative Q. So this is Q, this is negative Q. I'm going to plug in that quantity Q, that magnitude Q, divided by delta V. I'm not going to sum up the values. It's just going to be Q. Kind of like when we were dealing with a parallel plate capacitor, how we had positive eta and negative eta, but you just take eta. or Q over A of one of them. I just take the magnitude of one of the charges. But I do need to have the pair of them together. So, got a whiteboard problem for you guys. Let's say you need a 100 picofarad capacitor for science. You're going to make this out of two big metal squares. So you're deciding that it's going to be a square because it's a more appealing shape than a rectangle or anything like that. Right, so it's going to be L by L, and you have a tiny set of spacers to work between these two that are 0.2 millimeters thick. So that's your spacing between your two big plates. What length L do you have to get our 100 picofarad capacitor? So, first things first, I'm going to draw some really bad square plates. I can't use my square tool, I don't think, so instead, we'll draw... Oh, this is nasty already. Perfect squares. Perfect squares every time, right? And especially that they're going at the right angle relative to one another, all those parallel lines, absolutely. That should have been a little bit longer, shouldn't it? Probably. I don't know. I don't understand perspective drawing because I'm not an artist. But you knew that already. So let's go ahead and take a look at this thing. We have a total capacitance that we're looking for of 100 picofarads, which I'm going to rewrite real quick as 100 times 10 to the negative 12th regular farads, right? That'll help. Now, I also know that the side lengths are L and L, so at every point along this way, the area is always going to be L squared. The distance we're already given as 0.2 millimeters, so that's 0.0002 meters. And we've got everything we need. We're just going to take the parallel plate capacitor capacitance equation, E naught A over D. As long as everything is in standard units, farads, meters, all that good stuff, rearrange this thing to solve out for not A, but L squared. So C D over E naught would be equal to L squared, but let's go ahead and look at L instead, so we take a square root. My pen is all over the place. I'm getting all sorts of weird scribbles, and I'm not sure why. But anyways, we plug in all of those numbers, and we should find something like 0.0475. Of course, in standard units, so if we want that thing back in centimeters, 4.75 centimeters. So let's go ahead and rock through the end of this. So this entire time I keep talking about moving charges in different places and stuff like that. And clearly what we're doing is we're storing energy in here, right? We can all agree that batteries have some energy stored inside of them, right? Whether that battery has high energy or low energy, if we've been using it for some amount of time or something, but I think we can all agree that a battery is charged up, it's energized, it's got a high energy inside of it. If I keep describing capacitors as just really bad batteries, surely they too have some energy inside of them. How do we describe that energy? Well, we have this very nice useful equation right here. Q squared over 2C, or 1/2 CV squared, right? That kinetic energy kind of form shows up in all sorts of fun places. But where does this actually come from? How are we actually getting into this thing? Well, what it's doing is we're actually looking at essentially how much field is inside of this thing. Let me go to our simulation that we're going to use for the lab this week. Something like this. There's some cool things here, right? And we can see that we've got like a value for stored energy and plate charge and a few different things on this thing. So I've got 1.5 volts applied to my parallel plate capacitors. But what were to happen if I start to increase the size of this thing, and it's a little bit slow to react, but we can see the stored energy gets larger and larger and larger as we are able to put more charge onto these things, for one. And then if we look at something like electric field lines, Are those field lines changing in quantity or in magnitude at all? No, not really. In fact, it seems to be just about the same the entire time. But the big difference here is that with more and more and more field lines, more and more space for those electric field lines, we're seeing a much larger increase in the energy that we are capable of storing on the capacitor. To change the electric field, it actually does require some amount of energy. So let me get rid of these field lines again real quick. Let's look at what happens to the charges on each plate as I separate them away from each other. So this goes back to my thing originally when I said that remember that when the plates are close together, there's an attractive force helping keep all of those charges in place. If I have a whole bunch of charges, a whole bunch of positive charges just on one plate, they're really not so happy to be next to each other. But if I give them something nearby that's attractive that keeps them in place, that makes it a lot easier to get some more charge on there. So to move these charges, it costs some energy. Right? There's an energy transfer that has to be done. There's a potential energy associated with their placement towards that other plate. And when there's not as much force to change the field lines to move the charges, it does cost some energy. We can watch the stored energy be constantly changing as I move the plates' distance from each other. So there's some fun things in that, right? That's basically saying that to change an electric field, it costs work. It costs energy to do that. And if we go back to an old description like when we were thinking of light from 191, when we were considering things like light, we were talking about how it's a wave, and I said it's an electromagnetic wave, and I said don't worry about that, it's a wave, don't worry about a wave of what right now, we just need to focus on it's got an energy associated with that wavelength and all that good stuff, right? But light clearly is energy. Light is energy. As it radiates as any sort of radiating object, it's radiating light. Light is the energy. Light is a combination of an electric field with a magnetic field. And I know we haven't talked about magnetic fields yet, but basically what we're showing here is that change in electric field, that traveling electric field, there is an energy associated with that electric field. And if I were to increase the intensity of that electric field, like if I was using a laser to have more photons going all together like that, I would be increasing the energy that's traveling. All of this is essentially getting us down to this equation down here. We can go through these transformations, plugging in some of these other variables, but what we're trying to say is that there's this thing called energy density, which is the energy inside of a capacitor divided by the volume of the capacitor. So when I'm talking about the volume of the capacitor, I'm talking about this space in between my two plates. So in a case like this, we would see this as the volume would be equal to A times D, or for our problem specifically here, L squared times D, right? If you look at the electric field within that, you can calculate the energy density. You can find the energy inside of a capacitor based on that electric field and the size of the capacitor alone, which is a cool thing in its own right. But when we're asking where does the energy actually go, the energy is stored inside the field. To change the field, to bring the field there in the first place, it costs energy, and that's where it gets stored. It's a conservative force, so we'll get it back out later, but it costs energy to change that field. So, quick concept check. I've got a capacitor. I put 1.5 volts on it, and I record that it stored 2 millijoules of energy. If I disconnect it, discharge it, hook it up to a 3 volt capacitor, how much energy is on it now? All right, so here's what I need. The energy stored on a capacitor, the easiest way to write this one out right now is going to be 1/2 C delta V squared. If my change of potential doubles, if I now have 2V instead of 1V, I get a quadruple increase in the amount of energy. U2 will be 4 times U1, 8 millijoules of energy should be our answer for this one. So let's go ahead. I've got one more slide to talk about and couple more things to look at, but the last material we've got for the day is all about dielectrics. And if you've been going through all of the review problems before the exams, you'll have seen this once before. Dielectrics are special materials that are non-conducting, so they don't allow their charges to move, but they do have atoms or molecules inside that are able to be polarized. So what that means is that if I put a dielectric into a capacitor, what it's going to do is essentially dampen the electric field. Right? And the way that it does that is all those polarized molecules, they'll start to separate out a little bit. What was a neutral molecule will become negative on one side, positive on the other side, a dipole, right? And that dipole is going to be attracted, so I'm going to see the negative side of the dipole go towards the positive plate, which means that I've got essentially less charge to create that field at that place, right? The field gets weaker as I put the dielectric inside of the capacitor. That's not actually a bad thing, though, and it's a very useful thing. Because all of these things that I'm seeing here, so we just talked about a problem where we had 100 picofarads, and to get 100 picofarads, I had a 4.75 by 4.75 centimeter square. Think about that size for a minute, right? That's like the palm of your hand kind of size. That's not practical, especially when you're looking at, I'm opening up my various capacitors again. Something like this, as tiny as this thing actually is, if you can even see this, trying to angle it so you can actually see it, but it's kind of small between my fingers. This right here is 22 microfarad, orders of magnitude larger than the capacitor we just made. And the reason being, it's not just because of the fact that it's spiraled around, but it's because it uses a dielectric inside. There's a fluid dielectric between the two layers here. And by weakening that electric field between the two plates, you're actually able to store even more charge on them. Here's how it works. When I hook these things up to a battery, it is going to keep gaining potential until it matches the battery. If I were to have just vacuum between these two plates, if there was nothing between these plates at all, they've got a capacitance based on the size of those two plates. But without any sort of weakening of the electric field, if we think about that integral one more time, E times D gives us the potential difference between those two. So if we weaken the electric field, initially, if we weaken the electric field, and then we look at that voltage, we're going to see a smaller voltage difference between the two ends. So what we can do without changing the voltage, if we've weakened the electric field initially, we can put much more charge on it to create a much larger electric field between those two plates. Or, I mean, get up to our equivalent space again. So let's go ahead and take a look at this thing in a problem. I think that might be the easiest way. I can talk about this a little bit more. I've been tripping over my words a little bit today, so it might be a little bit easier if I've got some pictures in front of me. So let's take this idea. I've got a parallel plate capacitor made from two 5 by 5 millimeter metal plates, right? So a much tinier one, much more like what we've seen in those things. They're spaced apart by 0.1 millimeters and hooked up to a 9-volt battery. First, before I do anything else to this, what are the capacitor's potential difference, capacitance, electric field inside, and total charge? Then, let's say without disconnecting the battery, we slide a piece of mylar in there, which is a dielectric material. It's got that value kappa is equal to 3.1. That's called the dielectric constant. So that dielectric constant is 3.1 for mylar. We put it between the plates. We still have it hooked up to the battery. So I want you to think about what changes, what doesn't change. What are those same values now that we've put the dielectric inside? Okay, let's go ahead and start taking a look here. So I'm going to draw this thing with a diagram that we are soon going to become very familiar with, if you are not already familiar with, but a tiny little basic circuit diagram. So let me draw a bunch of bad lines first. So let's, oh man, the pen's doing weird things. Okay, let me try and do this by hand then. So let's imagine we have a battery, and this is typically how we would draw a battery. So the positive end this way, the negative end this way, or a source of EMF. I'm not a huge fan of that, you can tell. But anyway, so we connect this thing up. We've got a 9-volt battery, and it's attached to a parallel plate capacitor. Drawn like that. And you know what? I'm actually going to draw that just a little bit larger so that we've got a little bit more space to draw on this thing. Perfect. And somebody bent our parallel plate capacitor all out of line, but you know what? That's okay. So, when we start this thing, we're told that there's a 9-volt potential difference between the two. But here's a fun thing. And there goes the draw pad. Going so well. Here's the thing, though. Even in part B, when we've put the mylar between the two, since we're hooked up to a battery, this whole wire all the way through is a big conductor, right? The potential across that conductor better be the same the entire time. So what happens in between inside of the battery here, that's not connected necessarily, right? Those are separate ends. There is some separation between those two, and that's what's actually creating the potential difference. But all along the wire, all along like this red section here, this is all at plus 9 volts. And we would see the other end would all be at, let's call it 0 volts. And again, this is a potential difference as I've got this thing written out. So it might not be plus 9 and 0, and maybe it's 0 and negative 9 or something else like that. But it's fine. The potential difference is the most important part. But what it means, though, is that there's always going to be the same delta V is equal to 9 volts no matter what. As long as this battery is attached, our capacitor is going to have 9 volts of potential difference between those two plates, whether we have vacuum, mylar, grape jelly, no matter what we put in between those points, I'm always going to see the same potential difference. So, always, delta V is equal to 9 volts. Now, these other parts do have a little bit of separation. So we start with a parallel plate capacitor with vacuum in between, which means all of the equations that we've just seen work well for us. So no dielectric is what we start with here. No dielectric means that we're going to have capacitance is equal to E naught A over D. Those are values that we have from our problem, right? They tell us that it's 0.0001 meters apart and 5 millimeters square. So let's go ahead and add on to our list of always things. My surface area is going to be something like 2.5 times 10 to the negative 5th square meters. My separation distance D is going to be 0.0001 meter. So I plug all of those numbers in, and what do I find? 2.212 picofarads. A very tiny amount. Potential difference, still 9 volts, not changing. The electric field. Well, I can just say, okay, well, it's a parallel plate capacitor. It's a uniform electric field the entire time, and it's going from one plate to another. So this is actually surprisingly easy to find that electric field. We could have said ED is equal to delta V, or if we rearrange this thing, delta V divided by D, which we have seen all the way at the beginning today. We saw something very similar, right? Delta V divided by some delta X. In this case, it's D, the separation between those two plates. Plug it in. The negative sign I'm not worried about because I'm just looking for the strength. Since I'm only concerned about the strength, I'm not going to worry myself about the negative sign because, again, we don't actually, I've just drawn the picture like this, but I don't know whether the battery's flipped or what we're necessarily looking at. But this is the strength of the electric field. But we would get 9 times 10 to the 4th volts per meter. And then finally, for the charge on the capacitor, we'll go with our old definition. C times delta V. To find 19.91 picocoulombs. So those are our three values for a regular parallel plate capacitor. Now, part two of this is let's insert a little bit of Mylar. So I'll do that in green. Mylar's a polycarbon material that gets used in a lot of different places. But anyways, the Mylar in between here has a dielectric constant of 3.1. So that means we're going to go over into a lot of our dielectric equations. First, we start with the capacitance. Capacitance goes up when I put a dielectric inside. But what we can do, let me do this real quick. Since we already have all of these values for the vacuum capacitor, the naked capacitor, I'm going to call all of these E naught, C naught, Q naught, just so that we're all kind of on the same page. This was before we put a dielectric in there. There's the capacitor without anything else happening to it. Now, with the dielectric inside, we can say, okay, well, the capacitance would then be C naught times kappa for a total capacitance of 6.857 picofarads. I could do the same thing for my electric field. I would take the electric field that I started with, and I'm weakening my electric field. And what we end up with this one is, shoot, I lost my value. 2.903 times 10 to the fourth volts per meter. And finally, I could take my Q naught, not Q naught, Q of the new capacitor. And I'm going to do the same thing here. I'm going to say C times delta V. It's just the easiest way to deal with this thing. I should find 61.71 picocoulombs. But I do weaken the electric field, and that might not be, if we needed that electric field for anything, surely that's not a fantastic thing, but the main point of a capacitor is to store a bunch of charge for us, to put that charge there to take out later. So it doesn't really matter what happens to these other values. We are trying to do whatever we can to maximize Q, and that's the point of a dielectric. And it's why we can get these very, very tiny capacitors to store huge amounts of charge as compared to if we had put no dielectric in there in the first place. Okay, before I get, yeah, it is increased. Yeah, by putting the dielectric in there, the dielectric's entire purpose is to be able to put more charge on the capacitor. Without changing the capacitor itself, if you shove a dielectric in between those plates, the amount of charge you can shove on the capacitor goes up. So, the last thing that I do want to talk about here is not any sort of material. It's not a problem for you to work on at this moment in time, but it is a little bit of a guiding step on 26.82. And I bring this one up because a lot of people have issues with this one. But basically what this problem is going to be is we're going to make a parallel plate capacitor, but it's not a parallel plate capacitor in that same way. It is two concentric spherical shells. But what that means is that if I'm thinking about the surface area of one sphere on a layer inside, if I have some tiny piece dA and I go to the outside sphere, those areas do not match up. So it's not a parallel plate capacitor. The area is not equal between the two. Even though it's two plates pressed together, because those areas are different, we can't use our parallel plate capacitor equation. Instead, you've got to think about the definition of capacitance as we've given it here. And then think again about what we do. How do we find the potential on a surface? Where did that problem go? Here it is. How do we find the potential on a surface of a conductor, specifically a spherical conductor. Those two details will help you get through this one. Right? There's not a ton of crazy number crunching. There is a little bit, but there's not a ton of crazy number crunching. But don't try to jump right into it with a parallel plate equation. Use what we have already seen in a couple of these other problems to make this problem a lot easier to solve. So, a little bit of help so you don't fall into a common pitfall for this problem. But anyways, I think that's going to wrap it up for the day here. Yeah, next time we start chapter 27. So don't forget about the lab that we've got associated with this as well, where you get to mess around with capacitors and build a capacitor and slide in and out a dielectric and see all the different things that it does to a capacitor. So it's good fun. It's a fantastic little thing. I do recommend spending plenty of time just kind of playing around with the simulation, right? The lab is there to have you do a couple guided things, but then mess around with it a little bit. Have some fun. But yeah, that'll be it for me for today.